the usual, and then we can get started. Right. Let me start by sharing my screen so that we can discuss what we're going to do this week. And I have more than one screen, so it's a bit difficult to keep them all separate. Should be able to see my presentation. I can see it on my iPad, so I assume you can see it as well. Thank you for confirming. Right, so what are we going to do this week? Well, today we're going to wrap up the part on regression. So this has been quite a long chapter. And I can imagine that it's the third time in a row that we talk about regression. We've covered a lot that is starting to become quite a big bunch of things to remember. So what I would recommend is that you have the upcoming exam week where we will not do anything related to statistics, but take that week maybe to read the notes read the course notes. That entire chapter has all of the examples worked out. And then also you will have this week already on Thursday, the first PC practical. So you will get a chance to practice with all of these things. So in total, there will be no less than 3 PC practicals. So 1 this week, and then 2 after the exam week. They're quite long, and they really go into details about everything that we've covered. So during the PC practical or afterwards, if you feel like, hey, there's something that I don't understand about regression, then do feel free to reach out. There's also a small session on written exercises for, where's my pointer? Anyway, you can see the yellow box on my schedule there for the 5th of April. There will be a couple of written exercises as well for regression, but for the most part, this is an R-driven, a PC-driven set of exercises for you to do. Okay, so with that, let's dive right in, and let me maybe, if I can find my mouse on all of the screens. Let me stop sharing and switch back to my other screen. Sorry, I didn't want to share all of my screens. But I do want to, okay, how do I turn this on? Zoom is really giving me a hard time today. I do apologize for that. Right. Okay, so I want to come back to one thing that I said in the last lecture that I think I didn't explain quite well, and that is, how do you build a regression model by adding predictors one at a time? So what I'm going to do is I'm going to go back to the Shiny app that I showed you last time for multiple regression, and there we can click our way through building a model. And then I'll pull up the slide that I showed at the end of last time, and I'll discuss how, on a more involved model, how this works. And you'll see that the prescription, once you get it, is quite straightforward. It's adding predictors and then removing the non-significant ones. But you have to see it once in, like, worked out, And I don't think I did that well last time. So where's my browser? Let me grab my browser and share that again. So here we go. You should be able to see my Chrome. Okay, that looks good. And I want to come back to the data set that we looked at last time, where we had the growth of Japanese larches explained in function of mineral composition. And we had 3 minerals, potassium, nitrogen, phosphorus, as well as residual ashes, so 4 predictors, and then the outcome was the height. And last time we sort of built models in a quite ad hoc way. We said, okay, what's going to happen if we add another predictor or not? But let's apply this model building procedure that we can use to sort of see what predictors to include and which ones to exclude. So for the example in the browser, this is a very simple example. It's going to turn out that we need all the predictors. But for the example on the slide, where we have a bit more flexibility, a few more predictors, there it's going to matter which ones you exclude and which ones you include. So first off, let me disable both of the model terms. Okay, now why does this not update? Computers, they really annoy me sometimes. Okay, that looks already a bit better. Okay, so what I've done here is I've disabled both of the predictors, nitrogen and phosphorus. And what that leaves us with is a model that only has an intercept. So when it comes to predicting the length here, what our model says is, well, all of the trees are exactly, or I predict that the trees are all 196.5 centimeters. And if you look at the output of R, then what you see is the same thing. Well, we only have an intercept, and the intercept is at 196.58 centimeters. And if you compare that model to the data, obviously this is not a very accurate model, because we see the data has some trend in it, which our model clearly doesn't capture. It just says all the trees have constant height. So what do we want to do? We want to build a better model. And how do we do that? Well, we include terms one at a time. So let's try including nitrogen and see what we get. If we include nitrogen, now you see we still have a flat, we have a plane, but it's a plane now that's at an angle. And you can see the value of phosphor here on this axis that I'm pointing at doesn't matter. It's only the nitrogen that makes a difference. Sorry, I said that wrong. So, oh no, I said that right. Yeah. Okay. So if we look at the outcome, and we're going to spend a bit more time here looking at the outcome of the summary of what R tells us. So here what we see is that we've included nitrogen, and we have a certain estimate for the slope. And then the model says, well, that slope is significantly different from 0. P is 3.3 times 10 to the minus 7. And conversely, what we can do is we can also look at what happens if we include phosphor. And if we include phosphorus, we also get a model that is with a significant slope, now 3.51. And so what we can do is, if we want to do this really properly, we can say, well, okay, which one has the more significant, which one has the more significant coefficient? Well, it was nitrogen with a p-value of 3.3 times 10 to the minus 7. So very, very small. Okay, so that's good. Let's add that to our model. Now we have a model that's already slightly better than what we had before when we just had a flat plane where we thought everything is 196 centimeters. And now we can, of course, improve that model further. We can say, well, what happens if now we include the other predictors as well? So let's try adding phosphor to that model. And so we add phosphor. We get another coefficient in our model. We look at the p-value and we see, yep, adding that gives us a coefficient that is significant. P here is 0.01, so 0.1%, highly significant. And if we look at the plot, then we see that borne out, we have something that objectively captures the data better. So there's a question in the chat box that I would like to have a quick look at. So the question is, if we only have phosphor as a predictor, why does the intercept not become significant? That's an interesting question that I haven't looked at myself. So yeah, if we go back just for a second to the model only with phosphorus, then we see indeed the intercept here is not significant. P-value of 14.6%. And we also see that borne out in the estimate. So the estimate for the intercept is -69 with quite a big standard error. So the intercept is not significant. Why is that? To be honest, I can give you a good physical intuition for why that is. What you could do is you could include your intercept as a term to include or exclude from your model. But in general, what we want to do is we basically just include the intercept as a matter, of course. It's a bit tricky because the intercept sort of plays a slightly different role from the other coefficients. Usually, yeah, we have it in our model. We almost never look at the intercept except when it comes to predicting, and it's the other coefficients with the other predictors with their slope where we really look at the statistical test. So yeah, I'm going to hide a bit behind the math here to say include the intercept in your model no matter what, and then do the tests on each of the predictors. All right, so let me go back to the model that had nitrogen and phosphorus. So we've added phosphorus. We see that adding phosphorus gives us a new significant coefficient. And important, we see that nitrogen still stays significant. If we added phosphorus and we found out that, hey, nitrogen now becomes insignificant, let's say P equal to 14%, like we saw for the intercept, then we could exclude it at this point. But it is still significant, so we don't exclude it. We keep it in our model. And now we say, well, hey, that's a good model, but can we do even better? Can we add some interaction terms? Or can we add some quadratic terms, nitrogen squared, phosphorus squared, and so on? And the answer is yes. So here there's only one interaction term that we can add. So let's try doing that and let's see what the model output tells us. If we add that interaction term, then we get a new coefficient, a new p-value. And what we see here is, and this is maybe worth emphasizing, at the 10% significance level, this term is still significant. So it's 7.55%, the p-value. And generally what we do is to decide whether or not we include the term in the model, we look at the 10% significance level. We're a bit more generous with our acceptance than normal when we would do things at the 5% significance level. So we sort of want to cast a slightly bigger net. So at the 10% significance level, we include this term. And now wanting to look at here, now we see that phosphor and nitrogen have become not significant anymore. And you might say, hey, therefore we should remove them from our model, right? But the answer is no. If you have higher order terms, then you must leave the lower order terms in your model, even if they're not significant. So here we have an interaction term that involves nitrogen and phosphor. So therefore, we must have nitrogen and phosphor in our model, even though individually they are insignificant. And now if we had other predictors or higher order terms, you could continue doing that. You could add one term at a time and see, is it significant? Yes, I include it. Is it not significant? Then no, I move on to the next term. And in doing this, you could build up a more and more complex model. So you will do this in the practicals for a more involved model. But for now, let me put the Shiny app aside and let me just pull up the last slide that we had in the lecture of last time. So bear with me just 1 second. Okay, so this was the slide that we had at the end of last Thursday's lecture. And here we have the full model for the largest. So the Shiny app only had 2 because we wanted to show something in 3D, but the full model has 4 predictors, which would be a bit hard to draw. I can't draw in 5 dimensions, not yet. But we can, if we have 5 or more predictors, we can always look at the output from R to decide what we have to do. And so if you do this procedure that I just described on those 4 predictors, and you include one at a time and look at which ones are significant to include them or not, then eventually you will end up with the model that's shown on the slide, where you have potassium as an individual linear term, and then you have 2 interaction terms, nitrogen times phosphor and phosphor times residual ash. And if you look at the outcomes, then you see basically that we have the 2 interaction terms, nitrogen and phosphorus and residual ash. And okay, I have to dive into the numbers a little bit. So here, if we look at our p-values for those 2 terms, then what do we see is that they are both significant at the 10% level. So significant at the 10% significance level. So one is 5.3% and the other one is 1.9%. And now if you look at the individual terms in your model, nitrogen, phosphor, potassium, and residual ash, even though some of them are not significant just by looking at p-value, so for instance, nitrogen and phosphor, you still have to include them in your model because you have interaction terms that involve nitrogen and that involve phosphorus. And now the last thing that you might say is, hey, okay, I get it. I need to include those terms in my model, but where are they in my R call? I don't see them. Keep in mind that R is a little bit forgiving with how you specify your model. If you write something like nitrogen times phosphor, R will already include nitrogen and phosphor in your model. So it will automatically include the lower order terms. You don't have to write them. And so, yeah, if you look at the the output of the model, you get something where the highest order terms are significant. They influence what is included at the lower order, and the end result is you have a model with an intercept, and then 4 linear terms for each of the minerals, and then 2 interaction terms, two cross terms. So I wanted to just come back to that because I think we glossed over that a bit, but I hope this gives a better understanding of how we build these models step by step. We will see a couple of these model building procedures again this lecture as well. Okay, so with that, we can then go back to the topic for today. And that is, we were talking about outliers at the end of last lecture. And let's maybe briefly recap what exactly we said there. Okay. So we looked at diagnostics to basically, or we want to understand what makes observations in our regression model significant, or what makes observations, to use maybe a better term, what makes observations influence or have a high influence on the outcome of a regression. And we discussed this a bit handy-wavy at the end of last lecture. We said, like, if you have a point that's very far away from the trends that you see in the data, then chances are that point is going to have an influence on the regression line or the regression surface. And we also discussed, hey, it's sometimes not easy to see on a scatter plot what an outlier is, or which points have high leverage, or which points are important. So we need strong or stronger tools to do the job for us without having to look at a regression, without having to look at a scatter plot. So let's look at some of those tools a bit more in detail. And I have to say, for some of these tools, there are computations lurking behind the surface or beneath the surface that we can't do ourselves because we don't have the required machinery. But we can at least discuss what do the tools tell us and how are they useful. And so the first concept is leverage that we will be looking at. And what leverage basically tells us is so a point with high leverage is a point that's where making small changes in the observed value is going to have large changes in the predicted value. So a way to think about this, and I will try to make this more clear with let's maybe try making a small sketch. And I have another web app to show, which will sort of drive home this message a bit more, which will make it a bit more visual to see what's going on with leverage. So let's say that we have some points, some data points, and we have a regression line like so. And we look at, let's say, we look at points that are very far away or relatively far away from the mean X value. So if we look at where do the X values lie, well, we see the mean value of X is going to be maybe a bit here. And so I'll call this X bar. And then the further away I get from that, I can take points that are relatively far away from that X. So let's look at points here and here. So this is far away from X bar. And if I take a point here with an X value that's far away, and I wiggle this point up and down a bit, then you can sort of see that wiggling that point up and down is going to cause the regression line to wiggle up and down by a relatively large amount. So if I move that point a bit downwards, then maybe I'll end up with a regression line that looks like this. Or if I move it a bit upwards, and maybe let me draw that in dashed to make the distinction with the so I have my points and so on. And so, yeah, if I move the point down, then maybe my regression line will look like this. And if I move the point up by a bit, maybe my regression line will look like that. And by contrast, let me try making the same figure here with similar dots. Sorry, that doesn't look like dots. Do that a bit better. Dot, 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 dot. Regression line. And now let me again indicate my X bar here. And now let's take a point that's close to X bar. Close to the mean of all the X values. Now, if I take a point with such an X value, let's take, say, a point here, and I move that up and down, then that will not change my that will not change my regression line by that much. It's maybe a bit difficult to sort of like really write down a proof for that, but you can sort of intuitively see if I change a point that's in the bulk of the data, then that's not going to have a big influence on the coefficients of the regression line. The line will change a little bit, but not as much if I took a point that's on the outside, that's far away from the mean. And so what this hints at is that points that are very far away from the mean X value have high leverage, and points that are close to the mean have low leverage. And this is an important concept, or this is an interesting concept to look at, because now if you want to know, is a point going to have a significant effect on the slope or the other coefficients of the regression line, what we can look at is the points with high leverage. One important thing is that it's not because a point has high leverage that it's automatically an outlier. That's not true. But high leverage can be an indication to say, okay, we need to go look at those points and see if there's something strange happening there. So let's maybe recap what we have on the slide. So it's a diagnostic measure to let you look at possible influential predictor observations, with the emphasis on possible. So it's not guaranteed that things with high leverage will be outliers. And what does the leverage measure? Well, the leverage measures basically how far the X value is from the mean X values, or equivalently, and via computation that we're not going to do, if I move my point up and down a little bit, how much is the prediction going to change? So that is one of the diagnostics that we will look at. And let's talk a bit more about the interpretation. So if we have points with high leverage, then typically we have predictor values that deviate strongly from the mean. So here we're talking about predictors, we're talking about X values. And it is possible, but not guaranteed, that that point with high leverage will have a large influence on the regression coefficients and hence on the prediction. And how large does the leverage have to be for us to be worried about things? Well, on average, the leverage will be P divided by N, with P the number of parameters and N the number of data points, the number of observations. And if we have leverage for a point larger than 2 times P over N, then that warrants having another look. So here, one thing to keep in mind is that there's one leverage value per observation. So each observation comes with its own leverage value. Okay. And we can draw, therefore, we can draw the leverage. And actually, I haven't told you how to compute the leverage. We can do that in R quite easily by using the hat values command. So if you build a model, let's call it M, using LM, and then you put a formula in there. If you ask for hat values M, then you will get the leverage values 1 for each observation. But we ignore how that's computed under the hood. And here we see, okay, we have the cutoff. We have, what is it, 2 times P divided by N. And this is for the largest example. So we had 4 predictors. 4 predictors, hence 5 parameter, 5, sorry, I can't find my words. We have four predictors plus 1 intercept, so 5 parameters, and we had 27 observations. So that works out to somewhere around 0.54, I think. This line is our critical line for when we consider the leverage to be extreme. And we see that there are 2 points with high leverage, point 1 here and point 4. But as I mentioned before, that means that we should have a look at those points to see what's going on, but that doesn't necessarily mean that those points are outliers. So in order to decide whether we have an outlier or not, we have to do a bit more work, or we have to come up with a stronger criterion. And one of those criterions, we'll see 2. One of those criterions is called Cook's distance. And basically what it does is it tries to figure out what the effect would be of an outlier. And you can sort of intuitively think about that yourself. If you had to come up with a criterion for, is a point an outlier, is a point going to have a significant effect on my regression line? One thing that you could do is you could look at 2 models. One where you have all the observations, including the outlier, and another model where you have all the observations minus the outlier. And then you compare, well, what predictions does my model A give? What predictions does my model B give? And if those are very different, then I can probably infer that the point that I omitted is an outlier. So what we do is, there's no single Cook's distance or Cook value or whatever. There's one Cook's distance for each observation. And what that measure is going to tell you is how strongly do the predictions change if I omit that, that observation from my data. So to make it a bit more graphical, let's say we have some observations like this, and then one that's, well, obviously an outlier. So let's call this observation I. And if we include that observation in the in the data set, maybe we have a regression line that looks like this. So it captures the upward trend, but you can see the regression line is pulled down by the presence of that that outlier. So let's call that model A, and then let's build another model B. So without observation I, and I will try to draw the points in the same location as they were before. So something like this. But now we do not have that observation I, so we do not include it in the model. So not this one. And then if we omit that, you can probably guess what's going to happen to the regression line. Is going to jump up and is going to nicely capture the other points. So now, how do we compute Cook's distance? Well, we look at the predictions for each of the observations under both models. So we look at for each data point, what are the predictions that I'm going to make? So this, and this, let's say. And now I look at model B without the observation, without observation I, and I again look at the prediction. So here, and then okay, also for observation I, even though I didn't use it in my model, I also look at, well, what does the model predict, which is probably going to be this point here. So the green crosses are what does the model think those X values correspond to. And now we get n predictions from both models, one for each data point, and we compare those predictions. And you can see that down below here in the fraction. So we take the difference between the predictions under both models. So these are the predictions from model A, and these are the ones from model B. And we take the difference and we square, because we're interested in the magnitude, not the sign, and we sum them all together. And so if observation I does not have a large effect on the regression line, if the regression line doesn't change a lot, if we omit observation I, then those differences are going to be small and the numerator is going to be small. If we have a genuine outlier, then the regression line is going to change by a lot. And hence the predictions are going to change by a lot. And those squared differences are also going to be quite big. So your Cook's distance is going to go up by a lot. That's sort of the intuition that goes into things. And then to finish the computation, we also have to divide by, or we divide by P, the number of parameters, times the mean squared error. So again, we take the residuals squared divided by the number of points. Why do we do that? To normalize Cook's distance. So if we just had a sum of squares, then that would grow if we had more data points, but we want something that is in a nice tight range that we can say something about. So maybe just to draw two more figures. So what is the intuition? Why do we care about Cook's distance? So if we have, again, I'm going to try drawing some points and hopefully make things schematically clear. So let's say we have an outlier here, and we look at the regression model with the outlier. So this is with, and this is without, and this is our outlier. So here we see that the regression line changes a lot. Hence, predictions change also a lot, and therefore di is going to be big. And by contrast, if we have a point that's not an outlier, let's say we look at this point right here. So first we look at this point, now we look at that point. That's probably not going to be an outlier under any normal interpretation of the word. So if we look at the regression line with the point, we may have this line, and without a point, if we omit that point, the regression line is going to change a bit, but maybe not a lot. Let's say it's this, so without. And here we have the opposite, so regression line doesn't change a lot, hence the predictions don't change a lot, and therefore di is going to be small. So you look at Cook's distance to decide, is a point going to be an outlier, yes or no? And now we have our Cook's distance. So it's a number that tells us how likely is a point to be an outlier or to have something going on that changes the regression. Now we want to turn that into a genuine yes or no criterion, or like a diagnostic where we could say, look at that point. What we can do is we can actually make use of a fact that follows from the definition of Cook's distance, and that maybe it's maybe a bit technical, but if we look here at the definition again of Cook's distance, it's basically a fraction, and we have a sum of squares in the numerator, and the mean squared error in the denominator is also a sum of squares. So if you think about, we have something that looks like a sum of squares in the denominator and a sum of squares, sum of squares in the numerator and a sum of squares in the denominator. That may ring a bell. When we looked at ANOVA, we also said, hey, we want the variation between the groups to be small compared to the variation amongst the groups. And we quantify that by saying, if we have such a quotient of variations, we are typically drawn to looking at an F distribution. And it turns out that Cook's distance is also going to follow an F distribution. So if you're not sure anymore about what the F distribution is, have a look in the course notes. But it's a distribution that has 2 degrees of freedom. And here, the degrees of freedom are the number of parameters, and then n, the number of observations minus the number of parameters. So exactly how we get to that F distribution doesn't really matter. But what we can do is we can now use it to say, what do we consider to be a large value of Cook's distance? Well, if it surpasses the 50% percentile of Cook's distribution, then we say, oh, hey, this is a point that you should be looking at. So in other words, if we have our F distribution, and let's say we look at our 50% percentile, so that's going to depend, what that value is of that percentile is going to depend on the parameters P and N, but we can calculate it with R or with a table. So this is going to be my 0.5 percentile. If my Cook's distance is larger than that, if it's on the right-hand side of this value, then I have cause for saying, okay, go and look at that point. Okay, so in the analysis of larges, if we include the interaction term, we have 7 parameters, 4 predictors, 1 intercept, 2 interaction terms. We have 26 data points, and therefore we can calculate again with R probably most easily we can calculate that the percentile is 0.94. And if we look at the Cook's distance of the first observation, remember that one also had high leverage, then we find 1.5, which is obviously larger, corresponds to the 77% percentile. So what does that allow us to say? Well, it allows us to say that first point, yes, that is a point that has a large influence on the regression coefficients. If we omit that point from our analysis, our regression is going to change by a lot. That's what Cook's distance tells us. And here we can also plot the Cook's distance for all of the points, and you see this borne out quite nicely. So again, we have our point 1 with high Cook's distance. But now also look at point number 4 here. This has high leverage. That was something that we saw on the previous plot. But now we see it has low Cook's distance. So it will not have a large impact on the regression coefficients. And we can also look at the outputs that R generates for us to find out where Cook's distance or what Cook's distance is, and what the outliers or possible outliers are. And for that, we can look at the fourth plot here in our output. So we already looked at plot number 1 last time for linearity, and then plot number 2 for normality of the residuals, plot number 3 for homoscedasticity, and now we're going to look at plot number 4 for outliers. And here what we have on the x-axis, and it's sadly cut off, on the x-axis we have the leverage, and on the y-axis we have the residuals. And what we see is we again have points with high leverage. This is probably point number 4 here. But you should maybe focus on this point here. It's not 10. It doesn't say 10. It's an O, a dot with the number 1. And what we see furthermore on the plot are these dashed lines. And these dashed lines indicate Cook's distance. So it's actually written on the figure here. And the way to read this plot is that basically anything that is to the right of the dashed lines is an outlier. So you look to the right to find your outliers. And likewise here, points that are to the right of this line give you your outliers. And that again confirms, just as in the previous plot, that we have one outlier, 1 point with high leverage and high Cook's distance, point number 1. And then one more criterion, and I will be quite, this will be quite similar to Cook's distance, and then we'll have a look at the practical example and take a break. One other criterion now that we can introduce is this DF betas concept, and this sharpens a little bit the intuition that goes into Cook's distance. So with Cook's distance, what we did is we looked at the influence of points on the predictions. So as a matter of fact, to put this in a different way, we look at the influence of points on the entire regression line. And now with df betas, what we're going to look at is again the influence of a single point on each coefficient of the regression model separately. So this gives us more information. So Cook's distance just says, okay, this point has a large influence on the line, but now df beta is going to say this point has a large influence on the line, yes, but it does so through this coefficient. If we change this point right here, if we omit it, then this coefficient in our model is going to change by a lot. So it makes things a little bit more tricky to sort of tabulate, because now what we have is we have not just one value per observation, but we have p values per observation. So for each observation, we get a vector, one influence on the intercept, another influence on slope for parameter 1, slope for parameter 2, and so on. And how do we construct this measure? Well, we use an idea that's very similar to what we used for Cook's distance. We look at two models, and now I'm not going to draw it. It's the same picture as before, just slightly different interpretation. We look at two models, one with the observation I and one without. And for each, we compute the regression line or the surface or the model in general. And now we grab the coefficients of the model. And what we do is we compare the coefficients from model A to the coefficients of model B. So that's what we have here in the numerator. Beta hat J is the jade coefficient, the jade slope or intercept of the model where we have all the observations, including observation I. And then beta hat J I between brackets is the jade coefficient of the model where we looked at all the data minus observation I. So we omitted observation I and fit the model to the remaining data. And now you can see what this gives you. If that difference is big, then we can say, hey, observation I is going to have a big influence on coefficient J. If it's small, conversely, we can say no, coefficient observation I has relatively little influence on coefficient J. And that difference by itself is already informative, but then we also normalize by using the standard deviation of the estimate for the full model, so the standard deviation of beta J. So here we have the difference of model coefficients in the numerator. And in the denominator, we have the standard deviation of beta J. And that standard deviation, how do you compute that? Well, either use the formula, which we glossed over a few lectures ago. So there is a formula and you can compute this by hand, or you look in the output of R in the standard error column and you grab that value. There's something more that the df betas give us that Cook's distance does not give us. Cook's distance was a sum of squares, so it's always positive or zero, but the df betas can be negative or positive. And negative means if we delete observation I, we increase coefficient beta. So you can see this, if the numerator here is negative, then beta J is less than beta Ji. So if we remove observation I, we increase beta, like we summarize here. And conversely, if df betas is bigger than 0, then the coefficient of the model where we deleted observation I is going to be smaller than the coefficient in the full model. So it causes a decrease in the coefficient. So we can, from the sign, decide, okay, is this going to increase or decrease my coefficient? And that's often useful information. For instance, if we want to know something about an association, just think about simple linear regression. The slope of the line tells us something about our association. And typically we want to know, okay, we have an outlier. Is that going to change my association in the negative direction, in the positive direction? Is it going to make it stronger? Is it going to make it weaker? So the df beta for that coefficient gives you that information. And so what do we want to look for when we have these values? So as a rule of thumb, when we compute these values, we want to look for a value that's higher than 1 in small to mediocre is not the right word here, small to moderate data sets. So let's say up to 50 data points, and 2 that exceeds 2 divided by a square root of n in larger data sets. And here we can again do that. So here what we look at is we have a plot now of our df beta for observation 1. So this is important. We will have in general, remember we have p values for each observation, 1 for each coefficient. Here on the plot, we look at the coefficients for observation 1. We have that p is 7. We have 7 coefficients in our model, and we've listed them here on the x-axis 1 through 7. And what we see is that 0.1 has a large influence here on coefficient 7. And let me just see if we can pull up what coefficient 7 was. Should have written this down. Do I have my full model here somewhere? I don't think I do. Okay. It is one of the interaction terms. So yeah, my apologies. I don't recall what coefficient exactly we've put here, but it is one of the interaction terms. So these two were both interaction terms. Then the 4 preceding ones, 2 through 5, were the coefficients for the individual minerals. And the first one, that was the intercept. So maybe someone who has the slides from the last section open can quickly tell me what number 7 corresponds to, but it's one of the interaction terms. So this gives us very detailed information into what the effects of an outlier is, because now we can pinpoint, like, it's going to change this coefficient in precisely this way. And so we can make that a bit more quantitatively accurate. What we can do is we can look at the actual coefficient. And yeah, so, okay, maybe let me just take a cue from my slide. Okay. no, yes. So okay, I've answered my own question by looking at the next slide. So the coefficient is that I just mentioned, number 7, is the interaction between phosphor and residual ash. So you can add that here. Phosphor and residual ash. Okay. All right, so let's play with that a little bit. In our full model, we found, and you can look at the model building step previously, we had a coefficient of about -600. And from the regression output, we also had a standard deviation or standard error for that parameter of 290. And now what we see on the slide here is, or on the figure, is that the DF beta for that extreme observation is about 2.17. So now we can use that to estimate by how much is my coefficient going to change if I remove that observation. And in order to do that, well, what do? I use my definition of DF beta. So I know that DF beta is the beta in the full model, and I will drop the J subscript minus the coefficient that I get if I delete the observation I divided by the standard error or the standard deviation. So in other words, what this tells me is that I can change that to read, well, if I delete my observation, my coefficient is going to become my original coefficient minus the standard error times the DF beta for that coefficient. And if I plug in the values, so I get -598 minus 2.17 for my DF beta times the standard error. This is my original estimate, and that should give me an, this is not going to be accurate, this is not going to be exact, but it's an approximation. This is going to give me an approximation of what my new regression coefficient is going to be if I remove that observation. So we get -1227. Okay, just a second. I just want to make sure that we have enough time. I have a quick practical demonstration. So yeah, let me maybe quickly wrap this up. So what we can do with that information now is we can have a look at what happens to our model fit if we delete that first observation. And so what we do here, we'll look directly at the model output. We won't look at any diagnostics. But here, what we do is we create a new data set. So this -1 notation, that is basically our notation for delete or remove observation 1. So we take our original data vectors and we remove the first entry from each of them, and we refit our model. And if we go look at our interaction term, the one that we thought was going to change by quite a lot, then we see, yes, it has changed. It has become something in the order of what we expected it to be, -1227. So it is actually -1225, but actually quite close. And now we have a new data set. We can reanalyze this model, and we can decide to remove terms or refit the model if we choose to do so. So let me maybe, I'm looking at the clock. How much do we have left? Okay. Let me maybe stop here with the slides and quickly show you an interactive demo, another one, and because it allows you to compare the criteria that we've established in sort of a more interactive way. And I will also share the link to the demo so that you can play with that afterwards. So I will put this aside, and then maybe we'll come back to this shortly after the break or afterwards. Okay. I'll stop sharing. And now I need to re-share my screen. That's what I want to do. Okay, you should be able to see my browser. It says regression outliers and leverage on top. Give me a shout if you can't. Otherwise, I will assume that you can. So it might be, actually, let me have a quick look at how this looks like on my iPad. Okay, so I hope it's legible because the font is a bit small. But what do we have here? Well, on the top plot, we have a scatter plot of 10 data points, each with a label. And then we have that red point that I'm dragging around now. That is going to play the role of our outlier. And on the bottom, we have 3 diagnostic plots. We have the leverage. And the dashed line here is 2 times P divided by N. So here we have a linear regression, and we have 1 predictor, so 1 slope and 1 intercept, so 2 parameters. So this line is going to be at 4 divided by 11, which is, yeah, I don't know how much that is, but it's wherever that red line is. In the center, we have Cook's distance. And the dashed line is, again, the cutoff is the 50% percentile of an F distribution with 2 and 9 degrees of freedom. So the 9 coming from 11 minus 2, N minus P. And then here we have the DF betas, but we have DF betas for the intercept, and we have DF betas for the slope. And I'm only plotting the DF betas for the slope because that's what I'm most interested in. So the slope is what I'm most interested in. And here I have that dashed line that is at 2 divided by square root of the number of observations, so 2 divided by square root of 11. Since this is a very small data set, I should have probably used the fixed boundary of 1, but I didn't. It's just going to make us look at more data, but that's fine. And now what I can do is, yeah, you've guessed it, I can drag the red point around, and I can see a bit what that does in terms of my diagnostic. So first, if I leave it here, I see that point has relatively high leverage, but not overly high compared to the other points. So in particular, I see point 1 here has much higher leverage than point 11, my red point. And that is to be expected because, again, leverage measures how far away you are from the mean predictor and how significant the predictions are going to change if you move that point around. And points that are further away from the mean have higher leverage. So that by itself is not enough to say that the red point is an outlier. But if we look at the Cook's distance, the picture looks quite different. So here we see, yeah, Cook's distance above the threshold. So yeah, that point is probably an outlier. It's going to have a large effect on our regression line. And intuitively, you should also sort of develop a bit of an intuition for what kind of effect. Well, that red point here, what is it going to do to my regression line? It's going to pull that line down. So it's like if this point was very far away, okay, and now I've lost it. So let me reload it. If that point was very far away, I could probably even change the slope of the regression line. And then last, the DF betas tell me something about in which direction is the slope going to change. If I omit that point. So here my DF beta is negative, meaning that the slope is going to increase if I delete the red point. And that makes sense because I just said the red point drags the line down. So if I delete that point, the line is going to go up again, so the slope is going to increase. And now let's move that point around a bit and see what happens. So if we move it amongst the bulk of the data, then yeah, we will probably not have such a significant effect on the line anymore and on the regression. And we see that borne out by the diagnostic. So the leverage didn't change all that much because I didn't change the X value. But now Cook's distance says, no, that point is probably not an outlier anymore. And the DF betas also say, well, it may be a very weak outlier, but there are other points that exceed the bounds. And likewise, if we move it to the center of the distribution, then we see now, yep, it's definitely not classified as an outlier according to Cook's distance and the DF betas. And now we see the point also has very low leverage because it is close to to X bar. And you can move the point around in the opposite direction. So now I managed to drag it off the screen. That's a usability issue of my webpage that is not entirely good. So let me try to do that again and just leave the point here. Okay, that's better. So now again, we see, yep, the point is classified as an outlier. And also the DF betas tell us, okay, the slope is going to increase by a lot if you remove that point. So once again, I will share this with you so you can play with it a bit if you don't already have that intuition. But I think you'll find that Cook's distance and the DF betas have quite a natural interpretation in how much does the regression change if the line change, if the point changes, sorry. Okay, so with that, it's 11:15 and I suggest we take a small break until 11:30. I saw there were a couple of questions in the chat. I will get to those after the break when we continue. So we'll take a small break until 11:30. And thank you for your attention so far. All right, we're back. So just a couple of questions to be addressed and then some things to wrap up. I'll share my screen again. There was a question before the break about the diagnostic plot. So here, let me be a bit more precise when we look at the residuals versus leverage plot. I will make this figure a bit more clear. So the question was, there are two lines on the plot, two dashed lines. Well, two sets of two. You have this line and this line, and then you have this line and this line. And if you look at the legend here, this tells you what the difference is. So the one that I'm shading now has Cook's distance equal to 0.5. And the other one that I'm not going to shade has Cook's distance 1. So what these lines represent are basically level sets of the Cook's distance. They're telling you if you go beyond this line, then your Cook's distance is higher than 0.5. And if you go beyond this line, then your Cook's distance is higher than 1. And the way to interpret that is that normally we want things to be, or at least for this plot, we want to look for things that have large Cook's distance. So we're looking for things that are sort of like in the upper right corner or in the lower right corner here. And typically we would say, oh, okay, the Cook's distance is greater than 1. So therefore we definitely must look at it. So if the points are beyond the two lines, then yeah, definitely that's a sign of a strong outlier. If it's beyond beyond Cook's distance 0.5, but let's say less than Cook's distance 1, that might still be cause for us to pause and look at the point, but we could say, oh, it's probably not going to be a strong outlier. It's a point of interest. It's a weak outlier in some sense. We should maybe have a look at it or think about it a bit, but it's not as strong. So in general, the further away the points are in the upper or in the lower right corner, the more outlier-y they are. That's so that's how to interpret those two lines on the plot. Okay, and then I just wanted to wrap up by talking about the model one more time. So assuming that we've identified our outliers, then there's two things that we can do. One we already discussed is we can remove that one outlier. And we did that before the break, and we obtained this model with indeed that change in the coefficient that we observed. And you can now look at the p-values of the model and see, okay, do any of the terms need to be removed? Are they now no longer significant or not? And it turns out that, yeah, none of the p-values indicate that some slope has become not significant. So in particular, we have, yeah, the interaction terms 0.8, 0.1. So these are significant at 10% level. And then the individual terms, yeah, they're all significant except for the phosphorus term, which is 20%. But we have to keep it in the model because we have an interaction term that also has phosphorus in it. So therefore, this one is not significant, but we have to keep it in because of the higher order interaction term. And this is the final model if we delete that observation. But we have to be a bit careful in doing that. We should only delete an observation if there's a good reason to do so. So for instance, if you look at your data and you decide, okay, I'm measuring babies and all of a sudden I have a baby that weighs 50 kilos, probably there was something wrong with the data entry, so I can remove that observation without losing any significance. But if you have an observation that is normal by any standard, then you you should probably keep it in your model, even if it is an outlier. With the Japanese larches, we've identified that observation 1 is an outlier. That does not necessarily mean that we have to remove it from our data set. I don't know what the values are, but if you look at a scatter matrix or a set of scatter plots and you pick out observation 1, chances are that it will have values for nitrogen, phosphor, potassium, and residual ash that are well within the range. So there will not be, in this case, a physical reason to say, oh, observation 1 is non-physical and has to be removed. So if that's the case, if you have an outlier and you say, hey, it has this really high impact effect on this coefficient, but I have no reason to remove it on physical grounds, then the other thing that you can do is, or that you should consider, is removing the term that is affected so much by the outlier. So in this case, what that means is the term that was impacted is phosphor interacting with the residual ash. So here, if the outlier is physical, so if there are no reasons to remove it, then consider removing the impacted term. So the term in the model that changes a lot based on that outlier. Why? Because we found that, hey, we have something that is that can change quite a bit depending on whether or not you include one or other observation. So therefore, that term is not well fixed by my data set, and therefore that is grounds for not including it in the final model. So in this case, that was phosphor and residual ash. So, and if we do that, then we get a new model. And now we have still our interaction nitrogen and phosphor. And we have our 4 individual predictors, nitrogen, phosphor, potassium, and residual ash. And now we can, when we fit the model and we look at our output, then we see, okay, nitrogen and phosphor stays significant, and therefore I have to have phosphor and nitrogen in my model, even though they are not significant, so 50% and 18% respectively. And if I look at my other terms, well, what do I see? Well, potassium is still significant, but now residual ash itself has become non-significant. And there's no higher order term that involves residual ash anymore. So therefore, I have something that is not significant and not protected by a higher order term. So therefore, I'm going to try removing that from my model. And if I do that, well, now I end up with a model with 3 predictors and an interaction term. And let's do a quick check of the p-values. So nitrogen and phosphor stay significant. So nitrogen cross phosphor stays significant. I have to include phosphor and nitrogen themselves, again, because they are part of the interaction. And potassium also stays significant. So in this way, I've built a reduced model. I've used my knowledge of the outlier to do so. And I have fewer terms than I had before, and terms that I think are going to be all robust against my outlier. So if we look at our final model, we can see that we compare our original leverage here on the left with our reduced model, and we see that that 0.1 now no longer has such huge leverage. That's already a good sign. If we look at Cook's distance, we see the same picture. So keep in mind, we have not removed 0.1. So that was an outlier for our original model. It's still in our data set. We've just changed the model to remove that interaction term. And now we see 0.1 here is a perfectly normal point, no longer classified as an outlier, very reasonable Cook's distance. And likewise, if we look at the output from R, the residual plots, we have good linearity. There's maybe a small quadratic trend that you can observe there. We have good normality. Homoscedasticity, again, you see sort of maybe a quadratic trend, but this is good enough as it is. And now in the residuals versus leverage plot, we see no point in the data set is classified as an outlier anymore. So we have nothing in the top right corner. And that gives us, basically what we can conclude is our finalized model for predicting the height of the Japanese larches based on those input values. And we have a reasonable good fit. Nothing is too influential, too outliery. So at this point, we can say our analysis stops and we have something that we can use for prediction or for quantifying associations. There's a question in the chat, how can we distinguish whether the graph has a pattern or no pattern? I will admit it's a little bit of an art, especially if you have real world small data sets, which in this case we do. It depends a bit how far you want to go, I would say. So for this case, you should accept that you will never get that line in the top left exactly flat. It's always going to wiggle a bit up and down. So there's always going to be some variability that you will not be able to capture. But you have to keep in mind what you can do. So one thing that you might try here is you might say, well, this is good enough for me. Or you might say, well, it's not good enough and I want to do something about it. So what you can do in that case is you can say, well, I haven't included any quadratic terms in my model. I haven't included potassium squared, nitrogen squared, and so on. So let me try including those terms in the model and see if I can get a better fit. So that is something that you can consider. So what I'm trying to say is there's no golden rule to say this plot looks acceptable and this plot does not look acceptable. It is a bit down to intuition and down to, if it doesn't look acceptable to you, what would you do in response to make it look better? If you can build a more complex model, you can try doing that, but you have to be a bit, you have to keep in mind that real world data is always going to have some patterns, so you'll never get something that exactly matches the data. So generally, what we do want to look for is we want to look for broad patterns in our diagnostic plots, and I'm just going to scribble on the figure. But what we don't want to see is, for instance, things that residual plots where the residuals increase uniformly in magnitude, because that means that there's really a trend that you haven't captured. And likewise for the scale location plot, if you have something with a clear trend, that's also cause for concern. And for the normal QQ plot, I think you've already seen this. You will always have some points near the end of the line that are not exactly on the line. That's acceptable. But what you don't want to see is something where the bulk of the data is off the line and then jumps like this, because yeah, that means that you have some significant skew in your distribution. I will erase that again because that was just for show. Okay. So with that, that gives us all we need to know about outliers. And now let's continue with the logical progression. So now we have a model that we think is as good as it's going to get. We've done everything and we're happy with our model. So now let's do something with our model. And so what can we do with our model? Remember, there's two things that we can do with a model. We can test for an association between variables. So is the size of your palm associated with your height? And how strong is that association? And we can also use our model for prediction. So if I give you a new tree that's not in your original data set, and I tell you what the level of ash and nitrogen and potassium and so on is, can you give me a prediction for how tall that tree is likely to be, and how confident are you about that prediction? Or if I tell you, oh, if you got a new student with hands that are 8 centimeters wide, how tall is that student going to be on average? What does your model say about that? And it's the second that we'll look at a bit more in what comes up next. And so here we do exactly that. We have our final model from the previous slide deck. And by the way, I have uploaded this slide deck to Euphora. It should be number 4 in a series of 5. So on Euphora, this is 7 regression 4.pdf. Okay, so we have our final model, and now I give you a new tree with nitrogen 1.9, phosphorus 0.2, and potassium 0.7, and I ask you, what does your model think the height of the tree is going to be? Well, very easy. We just use the estimates for our coefficients. We have the intercept here. We have beta nitrogen. We have beta phosphorus. And we have beta potassium here. And we have the interaction term beta nitrogen phosphor here. And we take all of those coefficients and we multiply the slopes by the corresponding values. So percentage of nitrogen 1.9 times the slope for nitrogen, and same thing for phosphor 0.2, 0.2, and 0.7 for potassium 0.7. And then yeah, also the interaction phosphor and nitrogen. And okay, you calculate all that out and you get an average height of the tree of about 163 centimeters. That is what we call a point estimate. A point estimate is a single number that tells you what your model thinks it is. Point estimates are useful, of course, but they're limited because we also want to know a bit how confident are we about that prediction. Could it also be 153 centimeters? Could it be 10 meters and 63 centimeters? How confident are we about that value? And so in order to estimate how confident we are about that value, we need to take into account where are the sources of variability in our model. What is the model confident about, and what is it not so confident about? And if we think back to all the way when we started with linear regression, with simple linear regression, there are basically two sources of variability. There's, first of all, the variability in the residuals. How tightly are your observations clustered around the regression line? So if I make a very schematic plot, how widely distributed are your observations around the regression line? So do you have something like this, or do you have something where the observations are very closely together around the regression line? So in the first case, we have high variability of the observations around the regression line. And in the second case, we have low variability around the regression line. And so for the examples that we've seen so far, we were able to look at the distribution of the residuals and estimate the variance and the standard deviation of the residuals. We had, for instance, that for the basal areas, the riparian tree density, the residual standard error was 1.01. And for the largest example, we had 35.55 for the standard error. And so that's one source of variability, but it's not the only source of variability. The other one is a bit squeezed in right here, but don't forget this one as well. The second source of variability is the precision with which we've estimated the coefficients of our regression line. So if I try to sketch that again, what do we mean by that? Well, the regression line itself, it's not when we build our coefficients, those themselves, the coefficients are estimates. If we had another data set, we would have a slightly different regression line, and that line could be different by a lot or by not so much. So our regression line in and of itself is also something that is subject to variability. And it depends a bit, like if we change our data, is our regression line going to change by a little, or is it going to change by a lot? But one thing is for sure, we know that, yeah, if we wiggle the data a bit, then our regression line is going to change, and we can quantify by how much. That's what the standard error of the slopes tells us. So here, a quantity that we should look at is the standard error for the slopes that we computed. Okay, so both sources of uncertainty are going to impact our prediction uncertainty, and in general, sort of weaving them together is quite complex. So thankfully, R is going to make things easy for us, and it's going to compute a prediction confidence interval for us automatically without us having to work through the formula. But it's worth taking a moment to think about the interpretation. So what we are going to define as a prediction interval is an interval around our point estimate that takes into account both of those sources of uncertainty, the line wiggling and how tightly our residuals are clustered around the line. And it's going to tell us with 95% probability what is a range that is likely to contain our true value given our prediction. So we will be able to not just give a point estimate, we'll be able to say beyond, okay, the person with hand size 8 is going to be 1 meter and 75 centimeters tall, but we'll be able to give a prediction interval of, let's say, 155 to 195 to say, with 95% confidence, we know that if we actually measure the person, their height is going to fall within this interval. And it's a bit hard to talk through it, but what do we mean again by that 95% probability that I have on the slide? It's the same interpretation as for confidence intervals, where if we make 100 predictions, and for each we draw the prediction interval, and now we measure the height of the person. So we've predicted the height, and now we compare the prediction with the actual height of the person. Then in 95% of the cases, we will find that their actual height is inside our prediction interval. That's the interpretation on that particular example. And like I said, R is going to make this very easy for us. If we ask for predictions with the predict command again, what we can ask for is either for a confidence interval or for a prediction interval. So note the argument here. And a little bit about the mechanics. How do you ask R for such an interval? Well, you have to specify what data do you want to get predictions on via the new data argument here. And I think I already mentioned this when we did simple linear regression. Syntax is a bit awkward. You have to specify a data frame of values that you want predictions on. So here we use the example of the basal area as a function of the riparian tree density. And here we ask for a prediction interval that tells us something about riparian tree density going from 800 all the way up to 2200. So this syntax in R is gives you a list, 800, 801, and so on to 2199, 2200. So for each of those riparian tree densities, we want to know what is the corresponding basal area and how confident are we about it. And then what you get back is another data frame with 3 columns. The first one is the fit, the actual prediction. And then we get a lower and an upper bound. And now the difference between these two outputs is that for the first one, we ask for a confidence interval. So for a confidence interval, we only take into account the variability in the regression line itself. And for the other outputs, for the prediction interval, here we take into account both sources of uncertainty. So the uncertainty in the regression line and the uncertainty in the residuals. And as a result, what you can observe is that we get the same predictions. That doesn't change. So for instance, this value and this value agree perfectly. But if you look at the lower and the upper interval, the confidence interval here is smaller than the prediction interval here. And that's something that you will always see. So if this is your point estimate, then your confidence interval is going to extend to a certain extend, and actually let's draw this in blue or in yellow for a change. The prediction interval is going to extend beyond that. This is the prediction interval and the confidence interval. And that makes sense because you have more uncertainty in your prediction interval. And in general, it's the prediction interval that we're more interested in, because we want to know, if we want to predict something, how sure are we about that? How much variability is there on our predictions? And we can do the same thing for our Japanese larches. We make a data frame with those values. We ask for a confidence and a prediction interval. And here we see the same thing. Confidence interval, again, is more narrow than the prediction interval, which is a bit wider, but the predictions themselves are the same. And now, so that's all good and well for prediction, but there's another way that we can understand the sources of uncertainty when it comes to doing prediction, and that is to decompose the variability in our predictions by looking at what we can call the variability around the regression line and the variability on the regression line. And what do I mean by that? Well, if we go look at a regression line here, indicated in blue, and we have our data points indicated by the black squares, what we can do is we can look at the corresponding predictions as given by the red squares on the line. So maybe to unpack it a bit, what do I mean by predictions? So I ask my model for each X value, what do you think the corresponding Y value is going to be? So since it's a linear model, it's going to give me something on the line. And now I can compare that prediction with the actual observation. So I can look at, well, how far are my predictions from my observations? So let's draw a few more, just a few that are distinguished, that are easily set aside. So in other words, what we look at is basically the residuals. And then what I have, so that's my plot on the left. That's just my data and my regression line. And now let's look at the plot on the right. So here I have two distributions of points. I have the distribution of my actual data points, and I have the distribution of my predictions. So this is the distribution of the data, and this is the distribution of the predictions. So what I do here in order to make this plot is I basically, for all of these points in the scatter plot, I ignore the X value. I just look at my hands. I take my scatter plot and I compress the X range. So I sort of mush them all together onto the X axis. And that's how I get my plot on the right, where I've separated them out between black points, data points, and red points, predictions. And what you can see is that, yeah, we have some variability in our data points, some variability in our Y values, that is to be expected, and some variability in our predictions and in our red data points. Again, that's to be expected. But now let's look a bit at how those distributions can change and what effect that has on our predictability. So let's take another scatter plot on the left where we have high predictivity. So what that means is what you think it means. Our observations are tightly clustered around our regression line so that the residuals are small. In other words, if we make a prediction, small residual means small error on my prediction. And you can see that on the left yeah, we have small residuals, hence small errors in our prediction. And if I look at what that means for my my data points, then what I see is on the right, I have high variability in my predictions and low variability around my line. And actually, I think I said one thing wrong here. Let me go back to the plot here. Pum, pum, pum. Yeah, I will have to make one change to my explanation. I am sorry for that. Okay, so let me erase that label and quickly describe it how it should be. So it's not just the case that I'm mushing everything together and then looking at the distributions. I was a bit led astray by how beautiful this metaphor was, but it's not entirely true. What I should be looking at is the distribution of the residuals versus the distribution of the predictions. So the interpretation of the red dots is correct, but for the black dots here, what I have is the distribution of the residuals. So what I do is I basically take all of my residuals and then I put a dot on the vertical line indicating the size of each residual. So I have residuals that range from about 1.5 to a bit less than -2. Okay, so with that, now I can come back to yeah, and good point. Remark in the chat box, what does the x-axis refer to, the 1 and the 2? These are just arbitrary labels. They have no physical significance. We just want to be able to compare those two distributions. We want to be able to put them side by side, but you can completely ignore the labels on the x-axis here. Okay, so let's look again at the scenario where we have low variability around the line. So my residuals are quite small now, and I see that also in my plot of the residuals. So the residuals cluster quite closely together. And by comparison, well, for my predictions, that hasn't changed much or at all. I still have wide variability. So what I want to see for high predictivity is basically tightly clustered residual distribution compared to the distribution of the predictions. So if the residuals are tightly clustered together compared to the actual predictions, then that's good for my predictivity. And conversely, if I have low predictivity, as you see on the left, so I have high variability in my residuals, then what I'm going to see is a distribution of residuals that's very widely spread out. That's what you have here. And then a distribution of predictions that is relatively tightly clustered together, as you see here. So in this case, we can compare the size of the two distributions to quantify how predictive do we think our model is. So that's a bit the picture to keep in mind. And now we can make that a bit more concrete with mathematics. So what we can do is, if we want to quantify our predictivity, is we can look at how wrong our model is when we, sorry, let me take that back. What we can do is we can try to quantify that insight that we derive from the pictures by having a look at how wide those distributions are. And so the way that we'll do that is we'll build up a sum of squares, and then we'll connect that to an error term. And so here what we do is we start by taking the difference between each data point, yi, the y value of each data point, and the mean value of y, so y bar. And we take the difference, we square that, and we sum all of those together to get a to get a certain quantity. And that quantity we call the sum of squares total. So what this does is it looks at our data points and compares them, or at the y value at least, and compares them to the mean y value. So, and now we can rewrite that in a certain way by, we can say, well, okay, let's bring the predictions into the picture and let's write this sum of squares as yi minus the predicted value, yi hat. And since I've subtracted by that and I don't want to change my sum, I have to add y bar hat again and do minus y bar like so. So in doing so, I have not changed my sum at all. But what I can do now in the next step is the following, and let me write that. Yeah, I will not write it out because it would completely fill up my slide. But you can sort of see what we're going to do now. We have that square of these four terms, and we're going to group them 2 by 2. So if we group these two and these two, and we work out the square, then what do we get? Well, we first get y, y hat. Let me underline which term goes where, although I think you've seen it. So we get this term squared, that gives us that. And we get this term squared, which gives us this term in the expression. And then, and it's important to just write it down and look at it for a second, we get also the double product, because if we work out a square, a plus b squared, it's a squared plus b squared plus 2 times ab. So get plus 2 times the sum of yi minus y hat I times y hat I minus y bar. So you also get that term, but you can show, and we will not do this calculation, that this term actually vanishes. This term is 0. So not each individual term, but the entire sum will give you 0. And that is a good thing, because what do we get from that? Well, we get that our sum of squares total is decomposed as 2 separate sums, the green one and the yellow one. And the green one we already know. Oh wait, the green one we leave as is for now, and the yellow one we already know. The yellow one is our, so yi minus hat yi, that is precisely the difference between the actual value and the predicted values. That's our residual. So what we end up with here is the sum of the squares of the residuals. And that's what we call the sum square of the residuals. And likewise, what do we get for the other term? Well, this is a new concept. So here, what we have is the difference between the predicted values, y hat, minus y bar, the mean value of y. And that we will call the regression sum of squares. So that's our green term right here. And what does that green term give us? Well, that green term is going to let us quantify the spread in the predictions. So remember, when we looked at these weird scatter plots side by side, we were interested in the spread of the red distribution versus the black distribution. And the red distribution is, well, how clustered together are my predictions? Well, the regression sum of squares is going to tell you precisely that. And what does the residual sum of squares tell you? Well, you know this from before. That gives you something about how far away are the predictions from the regression line. How well does the regression line capture my model? If the sum of squares of residuals is high, then my predictivity will be low. I will have a lot of variability in my predictions. And so now with these two terms together, we can derive a measure to quantify how well my model captures the data, and that is called the multiple correlation coefficient. And it's typically written as R squared, although it's not always the square of something. You should look at the definition to see what it is. The way that we define it is we look at the quotient of the regression sum of squares over the total sum of squares. And so why do we do that? Well, if we do that, the regression sum of squares tells us a bit how tightly are my predictions clustered together. The total sum of squares is basically all the sources of variation. So not just, okay, how tightly are my predictions clustered together, but also how much variability do I have beyond my regression line. And in establishing this quantity, what we basically end up with is a quantity that tells me how much variability is captured by my model, how much variability of my data is captured by my model. And to understand that a little bit more, let's look at the mathematics from a few different angles. So let's look at the third property on the slide here. So this R squared is always going to be between 0 and 1. Why? Well, we have that the sum of squares of the regression is less than or equal to the sum of squares of the total, because sum of squares total is sum of squares regression plus something else, and that something else is positive. So from that, it follows that R squared is going to be always less than or equal to 1. And why is it greater than 0? Well, sum of squares of the regression and sum of squares total are both positive. So therefore, our R squared is also going to be positive. And now let's look at some extreme cases. So if R squared is equal to 1, what does that mean? Well, from our definition, sum of squares of the regression is equal to sum of squares total. Because, yeah, if that fraction has to be equal to 1, then the numerator and denominator have to be the same. And from that, what does it say? Well, we know that sum of squares total is sum of squares regression plus sum of squares residuals. So in this case, the sum of squares of the residuals has to be equal to 0. Sum of squares equal to 0 means that every individual term has to be equal to 0. So what does that mean for our regression? If we have our regression line here, then that means that all of our residuals have to be 0. So our data points are exactly on the line like so. So in this case, we say our model perfectly explains the data that we're given. So we managed to draw a line perfectly through our data. By contrast, what happens if R squared is equal to 0? So if R squared is equal to 0, then that must mean that the sum of squares of the regression is equal to 0, or equivalently, the sum of squares of the residuals is the sum of squares total. And what does that mean by contrast? Well, where can I draw this? So if I sort of put it in here, did I write this down correctly? So yeah, the sum of squares regression is 0. And let's have a look at the regression sum of squares again. So if the regression sum of squares is equal to 0, then all of the green terms have to be equal to 0. So our predictions have to be equal to the mean value of y. So what that means is that all of our predictions are equal to one fixed value. So we end up with a regression line that is actually flat, where all of our predictions, and now I need to be a bit careful how I draw this, so I don't confuse the, let me not draw the predictions, let me draw the line and the actual data points, but my data points are so that nothing in my model, that my model does not explain anything of the data. So in the first case, I have perfect predictive power, and in this case, I have no predictive power. And another way to look at this is to say how much of the outcome does the predictor capture. So if I know the predictor, how sure am I of the outcome? How well can I predict the outcome? So in the first case, if r squared is equal to 1, with 100% accuracy, I'm 100% confident that I can predict the outcome. In the second case, even if I know the predictor, I am 0% confident that I can predict the outcome. And of course, in real life, it's not going to be either extreme. It's going to be something in the middle where you have some intrinsic variability and some variability that is captured by the model. Did I misexplain something here? Let me just double check. So I see a question in the chat box about why the regression line is flat. Let's maybe unpack that a little bit more closely. And since I don't have space on the next slide, I'm going to do it on this slide. So let's go through this calculation. So let's say if r squared is equal to 0, then what that means is that the sum of squares of the regression is equal to 0. And from the definition, then it follows that this sum of squares should be equal to 0. And if you have a sum of squares of things being 0, that means that each individual term has to be 0. So y hat has to be equal to y bar for all my observations. So what this tells me is that the model says for each xi, prediction yi hat is equal to y bar, which is a fixed value in and of itself. It's the average, the mean of the y values of my observations. Does that make sense? Jong-Won, does that make sense? So the follow-up question is, yeah, can we have r squared 0 even if the prediction line has a certain slope? So the calculation seems to bear out, yeah, no, in this case, yeah, what we basically have is that, well, at least the pictures are sometimes a bit dangerous to look at, but at least for simple linear regression, where you have a where you have a straight line, the fact that the difference that the predictions are all constant, yeah, means that your line is flat, that your slope is 0. But let me maybe think about that offline a bit more, because I think in the case of multiple linear regression, that analogy may not go up quite as well as we think it should. But yeah, for simple linear regression, the calculation carries out or tells us that, yeah, the line should be flat. So then moving on, so the multiple correlation coefficient for the different examples, we can calculate it ourselves using a formula, or we can look at the output from R, and sort of at the bottom of the table, you'll find sort of the R squared. And for the basal area example, we had 71.59%. So what that tells us that 79.59% of the basal area, the outcome, is explained by the tree density. And likewise, for the largest, the R squared was 88.36%. And here, yeah, same interpretation, the mineral composition explains 88.36% of the variability in tree length. So there's one finishing caveat here. So we want to have high R squared for prediction, because if we want to make a prediction, we want to be confident about the range of possible values. But we don't necessarily need high R squared for measuring an association. It could be that we have a weak association with low R squared, and that is perfectly fine. So now maybe for the last 10 minutes or so, some topics about diagnostics. This is slightly different. So there's a few things that we have to be aware of when we do multiple linear regression that go beyond the diagnostics that we've already seen, those 4 plots. And there's one thing in particular that we have to be mindful about, and that is correlation between 2 or more predictors. And why is that a problem? Well, if we have strong correlation between some of the predictors, then it becomes hard to estimate the coefficients of the model. It becomes hard to separate the effect of one predictor versus the other. And you can sort of imagine that, I don't know a good example off the top of my head, but if we have 2 predictors, x1 and x2, and let's say they are very correlated together, positively correlated, let's say, and we build a multiple linear regression model, it's going to be difficult if we find an association between x1 and the outcome y, the other way around. It's going to be difficult to discern, okay, if there's an association between y and x1, is it really because of y1, or is it because of x1, or is it because of x2? And so here in the example, that's sort of crystallized a bit more mathematically. So if we have a model with two predictors and two coefficients, beta 1 and beta 2, and if our predictors are exactly the same or very closely together, then what you can do is you can say, well, okay, x1 is almost x2, so I'm going to replace x2 by x1 and group these two coefficients, beta 1 and beta 2, together. But now what you obtain is a model with one predictor with two coefficients lumped together. So what R will be able to do is it can tell you what the sum of those two coefficients is, but it can't tell you what each individual coefficient is. And you might say, well, okay, that's not a problem. If I have correlated things, then yeah, I'll just do what the example says. I'll lump together the things that are correlated, and then I'll just estimate the sums of those parameters or linear combinations. And that is true. You can do that, but not as easily as you would hope. So this can be quite tricky. And so the reason that this collinearity manifests itself is that R will have a hard time fixing the coefficients in your model, and it'll settle on some parameter values, but with very large uncertainties. So it'll be very numerically uncertain about what the slopes and the intercepts in your model are. And that in turn, that uncertainty then drives, basically will make it very hard to draw conclusions from your model. It'll be hard to interpret the coefficients because the coefficients can basically change from one model fit to the next, or they can, small changes in the data can generate very large changes in the coefficients, and it'll also inflate your errors. So in general, having predictors that are correlated with one another is something to look out for. So yeah, once again, what does that manifest itself as, or what is the effect? Well, instability, very wide confidence intervals, very wide prediction intervals. Also, yeah, large changes, as it says on the slide, in the coefficients. If you add a predictor, so you add a predictor and all of a sudden everything in your model changes, that's a sign that it's unstable. Or what can also happen is that you change one data point or you remove a data point and everything changes. So that level of instability. So if you see that, then that's probably a sign to go look for collinear predictors. And likewise, what we can also look for is just correlation per se between the predictors. And you might have correlation between two different predictors, let's say age and health status or something. Or you may have, and you usually have, correlations and strong ones between predictors and higher order terms that involve predictors. So it's not unexpected that, yeah, if we have a term in our model that's X phosphor, and then we have X phosphor times X nitrogen, that those two will share some information and that they will be correlated. And what you can do in that case is you can center the variables. And what we mean by that is before fitting the model, you take your variables and your predictors and you subtract the mean from each variable. And one caveat here is that this only works for correlation between a term X, a predictor X, and a higher order term involving X. Or an interaction term. So it does not work for two completely separate predictors. For that, you have to do something more subtle. So in order to understand what that centering does, let's have a look at a couple of plots. So here we have scatter plots between x and x squared for a certain range. And as you can see, the correlation is very strong here. It's almost one, almost perfect correlation. And what we have on the right then is, what we do is we take here x minus x bar, so the average x, and on the y-axis we put x squared minus x squared bar. So we square and we subtract the mean square. And what you see is you get a nice parabola, which is not unexpected given that the y value is essentially x squared. But the good thing, at least, is that now there's no correlation, or at least no linear correlation between the two variables. And that's going to make it much more easy to disentangle what is the effect of x on our model and what is the effect of x squared. And we do see that quadratic trend, but that is fine. That is what the model needs to be able to distinguish between x and x squared. See, I'm almost out of power. Okay. We can also look at a more realistic example. So here we have a scatter plot matrix of the Japanese larches example once again. So we have our nitrogen, phosphor, potassium, and then our interaction term, nitrogen times phosphor. And we have this matrix, this grid of scatter plots, where each scatter plot by itself tells us something about the association between two variables. So for instance, the one that I'm highlighting in red here tells us something about phosphor on the x-axis and nitrogen on the y-axis. And if we look at these scatter plots, each by itself, we see, okay, nitrogen and phosphor, some correlation, but maybe not super strong. Nitrogen, potassium, also not super strong. But then if we look at nitrogen times phosphor versus, let's say, phosphor here, then we start seeing something of a positive relation. So here we would sort of single this out normally for concern because we see a clear positive correlation. I will admit to you there's also already a sign of a positive correlation, or at least a correlation between nitrogen and the interaction term, but let's focus on this one right here. So in that case, so in our example, there's some cause for concern. So now let's see what we can do about that. Well, we can center all of the variables. So for each of the variables, we subtract the mean, and then we use that as inputs in our model. And if we do that, then our scatter plots already look quite a bit nicer. Especially you see that in this case, there's between centered phosphor and centered phosphor times centered nitrogen, there's almost no correlation left. So that, of course, means that you have to look at a lot of scatter plots, and that's not always ideal. If you have 50 variables, you don't want to look at a grid of 50 times 50 scatter plots, even though the ones below the diagonal are the same as the ones above. That's far too much. So it's labor intensive, and it's also not a foolproof way of finding collinear variables. It can be that there's some correlation, not between two predictors, but between one predictor and a linear combination of two predictors. And then the scatter plot will not show you any correlation, but it will be there hidden in the data. And so what we can look at as a quantitative measure to detect this outsized influence is we can look at the so-called variance inflation factor, or VIF. And so what we do for that, or how do we define it? Well, again, we're going to have multiple of these coefficients. We'll have one for each predictor, and it's going to tell us something about how inflated is this one predictor versus others. And the way that we define it is we use a correlation coefficient, but not the correlation coefficient from the whole model. I will explain it in a minute. We take this RK squared and we put 1 over 1 minus RK squared. And what is this RK squared? Well, it is a correlation coefficient of a regression model where now we take the kth predictor and we look at all the other predictors and we try to predict the kth predictor. So we look at the regression model of the form xk modeled as a function of x1, x2, and so on up to xk minus 1. And then we omit xk itself, xk plus 1, all the way to xn, or x, let's call this xp. And so what do we expect? Well, if there's multicollinearity, then we expect xk to be explained by the other variables. So we expect rk to be high. So if multicollinearity, then xk is explained by other variables, and therefore rk squared is going to be high, is going to be close to 1. And now if we do 1 minus rk squared, that's going to be almost 0, and 1 over that, 1 over 0 is going to be almost infinity. So if the VIF is high, then that means that predictor k doesn't contribute a lot of information to the model. It can be explained itself as a function of the other variables in our model. And so in general, the VIF for each predictor is always going to be at least 1, but it can range up to infinity. Infinity if predictor k is perfectly explained by everything else in the model. And predicted here, you have to interpret in the sense of linear regression, so linear association. And so what this basically tells me is that it expresses how much larger the variance on the k coefficient is, so the coefficient of that term, than if the predictors were independent. So it's sort of like, think of it, this inflation factor as like expanding something. Like if my predictor was independent of everything else, the effect of that predictor would be 1. But now there's something else in the background giving this predictor a push. And as a result, this predictor has a higher influence, 10 times higher, 100 times higher, 1,000 times higher than what it would be if it didn't depend on anything else. And we want to be on the lookout for predictors that can be explained in terms of other predictors, because they will inflate, they will pretend to be more important than they really are. And statistically speaking, you can also show that these VIFs have a special interpretation as the average quadratic distance between the estimated and the true coefficients in the model, but we will ignore that for now. What you want to be on the lookout for is VIFs that are too large, and here we typically take a factor of 10. So I see that I'm out of time. I need just a couple more minutes to finish this off, because you will see this in the practicum, but I will go quite fast because we just have to look at some diagnostic plots and then we're done. So let's look at the example of the larches again. If we compute the VIFs, and you can do that with R, then before we center, so when we had the collinear variables, then you have VIFs that are quite large. So our critical value is here, and we have some that are more than 150. And if you do the centering, so you subtract the mean from every variable and then you refit the model, then you get much more manageable VIFs, with the highest being maybe 3 or 2.9 or something. And you have to be a bit careful when you look at your coefficients when you have centered your model. So before we could make this interpretation, hey, my slope is what happens to my outcome if I keep everything constant and I just increase everything by 1. But if we do the centering, then you have to keep in mind my model is going to be now in terms of these centered variables. So if I want to do prediction, if I want to interpret my slopes, I have to retransform by adding the mean before I take these coefficients at face value. So maybe just, one thing to point out here, in terms of the coefficients, a couple of things that we can see. So in particular, look at this phosphor term. So this phosphor term has changed, or the estimate has changed quite a bit. And keep in mind, that was one of the terms where we said, hey, phosphor is associated with the interaction term quite strongly. So we see a dramatic shift in the coefficient. And in this case, we can interpret it as saying like, oh, R has an easier job fitting this centered model than the original model. You see, on the other hand, some of the other coefficients barely change. And that is a good thing. And maybe I'm going a bit too far, but if we could do, assuming that our data are not perfectly collinear, like normally we would not expect this mean shift to have any effect on the transformation on the coefficients. We would expect to see exactly the same coefficients. But what happens is that R, or when you invert a matrix, like you have to do numerical calculations, and this collinearity will basically introduce some error in your calculations. And that's the cause of this instability that I gave you before, that I told you about before. And the fact that you have minus 1100 for phosphor, I am pretty sure if you change the data points a little bit, you can change that minus 1100 to quite different values. What happens by contrast, if you do center, then you give R something that it can much more easily fit, and it will be able to pinpoint the value more accurately. And it'll also do so with less, with more confidence. And you see that second point also carried out in the standard errors. So if you look at the standard errors, so for instance, for phosphor again, you see that the standard error drops quite a bit. So from 700 to 156. I will maybe skip over this example, but I will leave the slides up for you to have a look. There's another example here, predicting body fat as a function of different body measurements. So triceps skin fold thickness, thigh circumference, and mid-arm circumference. And here, what we will also see is that there's some correlation between the variables. So you see that in the scatter matrix, but here it's a bit difficult to remedy that, because now we have correlation between things that are not functionally related between two different variables. And correcting here, like centering, is not going to help you here. What you have to do is something more complex, like combining predictors in a certain way so that you have one combination that captures both, and one can do that with principal component regression, which is outside of the scope of this lecture. So I will not do this example. We will just stop here. And thank you for letting me go over time a little bit. One last thing, there's sometimes an advice to say, if you have strong multicollinearity, just throw away predictors. That can sometimes work, but it can also be an a manifestation, an illustration of strong confounding, where you have something in the background that influences two things at the same time. And depending on what you're trying to model, you have to decide, okay, do I have confounding and do I want to include both in my model, even though they are correlated, and maybe look for the thing that causes both, or do I want to ignore one or the other? So we will stop here. Again, thank you for letting me go over time just a little bit. And that concludes our part on regression. So from Thursday on, you will have a lot of time to play with regression. But in the meantime, if you have any questions, please do let me know. And wish you the best for the rest of the day, and see you after the exam week. Bye, everybody.